So this is the third trial for the linear regression model. Now we are going to take the maximum likelihood estimator approach. So the difference here is the second assumption, right? Conditional on x, the error term follows normal distribution 0, gamma 0. So first, I reparameterized theta. I mean sigma squared to gamma 0. So it will simplify the calculus because when you differentiate with respect to sigma, then always the square will be complicated or confusing. So I will simplify. And also this also implies conditional on x, the distribution of u does not depend on x. So x and u are independent, statistically independent. This is a stronger, more restrictive assumption than the uncorrelatedness. So automatically this implies conditional mean independence. Also, the variance of u is gamma 0. Okay, keep that in mind. And this is the normal distribution PDF, probability density. So we are going to use this density. And also I gave you the skewness and kurtosis, right? We are going to utilize them later. First, then let's think about log likelihood. So f of u is written as 2 pi gamma, 1 over 2 pi gamma, 0 times exponential minus yi minus xi prime beta 0 squared over 2 gamma 0. This was the density. So the log likelihood function, like beta and gamma, is log of that. So minus 1 over 2 log 2 pi minus 1 over 2 log gamma minus, so log and exponential cancels out, yi minus xi transpose beta squared over 2 gamma. Okay, and then differentiate with respect to beta. If you differentiate this guy with respect to beta, you get xi, so beta is only here, xi yi minus xi transpose beta over 2 gamma. And if you differentiate with respect to gamma, then gamma is here and here. It becomes minus 1 over 2 gamma plus yi minus xi prime beta squared over 2 gamma squared. Okay. Now let's do the second derivative. Second derivative with respect to beta is simple, minus xx transpose 2 gamma. And also the second derivative with respect to gamma is 1 over 2 gamma squared, and this is minus gamma cube yi minus xi transpose beta squared. Right, I believe this is right. And the cross derivative is minus xi yi minus xi transpose beta over 2 gamma squared. Okay, so it's complicated, but not that hard. Okay, now let's do the second question. So we are going to, let me see. We are going to think about the derivative theta 0 and theta. So this is derivative with respect to beta and derivative with respect to theta 0 with gamma. Okay, so then when you plug in theta 0 in here, it becomes, right, xi yi minus xi transpose beta 0 over 2 gamma 0. and this becomes minus 1 over 2 gamma 0 plus yi minus xi transpose beta 0 squared over 2 gamma 0 squared, right? And that becomes xi ui over 2 gamma 0, and same thing, ui squared 2 gamma 0 squared. Okay, oh, right. And then what we need is expectation of this times the same thing again. Okay, so this becomes so the first part, it is a matrix, ui squared xi transpose over 2 4 gamma 0 squared, and here we get 1 over 4 gamma 0 squared plus u to the 4th and 4 gamma 0 to 4th, right? And minus, denominator is 2 gamma 0 to 3 and ui squared. Oh, it's getting crazy. And their cross product is minus 4 gamma 0 squared xi ui plus xi ui to 3 over 4 gamma 0 to 3. Okay, same thing in here. Okay, so still okay, manageable, right? So first I'm going to take expectation. So we are going to take expectation of this matrix, and it is clear that this will go to 0, right? This will go to 0. And also we have to realize that normal distribution is symmetric, right? So the third moment is 0. This is 0. This is 0, right? So the off diagonal terms are automatically 0. Now, and then remember, expectation of ui squared is gamma 0, right? And also we can apply that here. And expectation of ui 4 to 4 is 3 times gamma 0 squared. So we are going to plug them in here. And then let's see. So this cancels out one of them. So it's xi transpose 4 gamma and 0 0. Here 1 over 4 gamma squared, 4 gamma 0 squared, plus 3 over 4 gamma 0 squared. 2 cancels out, right? And here this is gamma 0 and denominator is 3, so cancels out again. 2 gamma 0 squared and denominator is 1. So, and this in the end becomes 1 over 2 gamma 0 in the denominator. Alright? Alright, so that means in the end omega is x prime over 4 gamma 0 and 0 0, and here 1 over 2 gamma 0 squared. This was the answer to complicated but manageable, right? So then part C, we are interested in the second order derivative. Again, this is, so I will put theta 0. This is first, the first block will be beta, and the last block will be about gamma, and the cross product will come to here. Transpose should be transposed here. Oh, no, this is right. Transposed here, right? Okay. this is what we are going to calculate. And we already calculated the second order derivatives and just plug in theta 0. Then we get minus xi transpose 2 gamma 0. And here we get 1 over 2 gamma 0 squared minus ui squared over gamma 0 to 3. Same thing goes here. Excuse me, it's the, sorry about that. This is gamma term, it's not cross product. So that goes to here, squared over gamma to 3. And the cross product is here xi ui minus xi ui over 2 gamma 0 squared, and here minus x prime x transpose ui over 2 gamma 0 squared. Okay, just do step by step. I did the algebra on another paper, so you have to do it by yourself. And then take expectation of that. Expectation of this guy is simple. Like first, again, these guys are 0. So that is simple. And this expectation will be gamma 0, so will be cancelled out. So then first term becomes minus xi transpose 2 gamma 0 here. And it is 1 over 2 minus just 1 over gamma squared. So it is minus 1 over 2 gamma 0 squared. Okay, and 0, 0. This is H0. Okay. Then you see the pattern, right? So remember these. And then we will think about the bound. The second order derivative theta transpose is minus xi transpose over 2 gamma and 1 over 2 gamma squared minus yi minus xi transpose beta squared over gamma to 3 and minus xi yi minus xi transpose beta over 2 gamma squared and minus xi yi minus xi transpose beta over 2 gamma squared. Okay. Here we are going to bound each of them, right? So the first thing, 2 times gamma is, this is bounded by, so xi transpose is separate, but gamma and over 2 is separate, and 1 over gamma is bounded by 1 over lower bound of the gamma, right? So gamma is greater than CL lower bound, and then that means 1 over CL is greater than 1 over gamma. So using this, we are going to bound it this way. Okay, and so now then the second term, the denominator gamma is easily bounded, and also we are going to bound yi minus xi prime beta as, or rewrite this as xi prime beta 0 plus u minus xi prime beta. Okay, that is xi transpose beta 0 minus beta plus u. So how we are going to bound it? We bound, say, xyi minus xi transpose beta over 2 gamma squared will be bounded by, so x transpose beta 0 minus beta, it should be also taken like plus xi ui and divided by 2 times CL squared. Beta is also easily bounded by CL, right? And beta 0 minus beta cannot be greater than 2 times b, right? So because we learned beta, norm of beta is less than b. So that means that the maximum possible distance between two beta is like 2b, like plus b minus b can become 2b with the distance, right? So that's how we do n over 2cl squared. Okay, and then this term is similar, right? So 1 over 2 gamma squared is bounded by 1 over 2cl squared, so that is not a problem. And the other side, yi minus xi transpose beta squared will be bounded by, similarly, like xi transpose squared beta minus beta squared plus u squared plus 2 times xi ui times beta minus beta 0 minus beta. So it is we did this in another question, so we can bound it like that. Okay, and of course denominator gamma to 3 is also bounded by CL to 3, so everything is bounded, right? So then in the end, what we need here is only expectation of this, and this same thing, and this are bounded, right? So then we get this. Then finally, so as I said, just summarize all the things, and if expectation of this is finite and expectation of this is finite, then we have the bound, right? And this is also assumed by normal distribution, right? Because u is normally distributed, so that's not a problem. And then, so we have proven all the things. Now let's see the asymptotic normal distribution, part E, the question E. So to prove the asymptotic normal distribution, we have done a lot of things. First, we have to check whether theta 0 is the maximizer, unique maximizer of expectation Li. This is Fisher's proof. Fisher, by the general theory of maximum likelihood, always this is true. And second, theta 0 is compact, right? We assumed several bounds, so automatically we assumed beta is bounded and also gamma is bounded. So we do not have any problem with compactness. Okay. And then 3, L is continuous. This is trivial, look by the functional form. And fourth, dominating function for the second derivative, right? Supremum of this guy and then take expectation is finite. We just proven here. And 5, H. I didn't show that it is H is non-singular. I forgot to mention that. And 6, you calculate omega, and then we will do this. Okay, H was, where was it? H was this guy, and this is obviously non-singular first. Gamma is strictly positive, so it does not affect the singularity. And we know by the full rank assumption, one of the assumption is this full rank assumption, xx prime expectation should be non-singular, okay? And then the whole matrix is a block diagonal matrix, right? So this block, diagonal block are invertible. Each of them is invertible. So then the whole matrix is invertible, right? I'm using the theorem that, like, lemma A1, A2, if you think about this kind of matrix, then A inverse is A1 inverse and A2 inverse. Okay, so that means if A1 inverse and A2 inverse exist, then A is also invertible. That is pretty straightforward. And then now let's collect all the information. Omega was, I forgot. I didn't write it down. So this guy, omega was xi transpose over 4, 0, 0, 1 over 2 gamma 0 squared. Okay, and then h is here. Oh, by the way, I forgot gamma 0 here. And h0 was minus xi transpose 2 gamma 0, 0, 0 minus 1 over 2 gamma 0 squared. Okay, so, and then we know the MLE converges to normal distribution 0 V, where V is H0 inverse omega H0 inverse. Okay, and then let's think about its inverse. Its inverse is pretty simple. Just its inverse is its inverse and its inverse. Okay, and then we can calculate this. This becomes here, right? We will get xi transpose inverse, gamma 0 to inverse. This will be the final part multiplication, final product, and here we will get 2 gamma 0 squared in here. And remember, this is gamma 0 expectation xi. Here expectations are all dropped. Expectation inverse, which is beta. Basically, this is theta sigma squared. So this is the OLS variance. And interestingly, this is the, so if you use sigma squared, it is sigma fourth order. This is the variance of sigma estimator. Okay, so the variance of the variance estimator is 2 times sigma 0 to 4, right? So, and what we just get is basically this is the same variance as the OLS estimator, but I did not use the closed form solution at all, right? So the point of this general theorem is to prove the general the variance, to show the variance without using the closed form solution. And the last part is how we can calculate that. How we calculate the variance, right? Variance of beta hat is approximately 1 over n times gamma 0 times expectation xi transpose inverse, and variance of gamma hat is approximately 1 over n 2 times gamma 0 squared. Okay, and then the problem here is, first, gamma 0 is unknown. We do not have gamma 0, so then idea is we just use gamma hat here. It's and also we have to replace the expectation with sample average. That's all, right? So our estimated variance for the estimator of beta is this guy. Okay, and the estimator for the variance of the variance estimator is okay, right? So this is it.